All right, today is lecture number 14, durability number 3. So this is our last class on concrete durability. Okay. We'll discuss software attack and concrete durability in general. So here is a picture of software attack of concrete. The software may coming from underground, the soil. Okay. We may see spalling of the concrete due to formation of echingi. Okay. And we learned software attack when we discussed type 2 cement and type 5 cement. Okay. Actually, software attack is a blanket term covering different reaction between production of C3 hydration, which is the one we know, and sometimes even CSH can be affected. The source of sulfate ions can come in from groundwater, seawater, or industry runoff. Okay. So then when concrete has software attack, we may see expansion and cracking due to formation of echingi. Okay. Or sometimes CSH may also be degraded. Okay. So depending on the type of software attack. Okay. So sulfate-bearing solution from outside of concrete can penetrate in the concrete, okay, only to a limited extent, unless the concrete is very permeable. For example, the water-cement ratio is very high. If the permeability of the concrete is not high, the concrete is very tight, it is hard for the solution to penetrate and do the damage. If the concrete is permeable, the pores are large, the porosity is high, and the pores are interconnected. Okay. And then that make the solution easy to penetrate into the concrete. Okay. And here's that evaporation of at the surface exposed to air can introduce the suction, which leading to the continuous movement of groundwater through the concrete. Okay. What does that mean? Let me draw something for you. Okay, so my iPad. All right. Share my iPad. Okay. So you can see my iPad, right? So let's say this is the concrete. Okay, so the concrete is on the ground. And on the ground, we have sulfate. Okay. And also we have water, with sulfate solutions. Okay. And when the concrete is porous, the water will evaporate. So the concrete on top of the concrete close to air will be drier compared to the concrete here. Okay. So that will form a gradient in moisture. Okay. So that's how the suction can lead to the continuous movement of groundwater through the concrete. So the sulfate-bearing groundwater in concrete can cause precipitation of ethylene, okay, as we know of. The ethylene will deposit within the concrete. Okay. So the ethylene form, the volume will expand, so the concrete may crack. Right. So this is a classic sulfate attack we know of. Okay. Continuous movement of water will dilute the normal hydroxide ion concentration. So that means the pH level will be lower. Okay. And when the pH level drops below a certain value, okay, which is 12.4. So 12.4 pH level is the saturation of hydroxide. So below that, the calcium hydroxide will dissolve and leave the concrete. So that it will leave empty space. The pores will be empty. So that's another effect for sulfate attack. And lastly, the CSH may lose some of the calcium, and the CSH will become punky, which means the strength of CS will be lower. Okay. So that is depending on the type of calcium, such as calcium, magnesium, or sodium. This is the concrete footing for air conditioner. Okay, so the footing is in touch with the ground. If the ground has sulfate, we may have sulfate attack like this. So we can see some cracks and spalling of concrete. A concrete post, which also from the ground. Okay, you can see the concrete above the ground spalls off quite a lot. Concrete further up is okay. And the so-called adduction, which is the suction of underground sulfate solution. Okay, so the salt from groundwater can pass entirely through the concrete and deposit on top of the concrete as efflorescence. Okay. In a moment, I'm going to show you a picture of that. For the efflorescence, if you do an XRD analysis, it shows sodium sulfate, sometimes sodium calcium sulfate. Okay. Sometimes we can also find gypsum in efflorescence. As we can see from here, this is the sodium sulfate efflorescence on the evaporating surface due to the suction movement of ground solution. So depending on the type of sulfate solution, we have different type of sulfate attack. Okay. For sodium sulfate, it should be Na2SO4, right? Sorry. So we have two equations account for the sulfate attack. The first one is calcium hydroxide react with sulfate ions. It forms gypsum. Okay. So that will account for 120% increase in solid volume. So the concrete can crack because of that. The second one is what we know of. So AFM with the gypsum plus water, we have formation of ethylene. That is after concrete hardens, that will cause concrete to crack. So that is actually 55% increase in solid volume only. So if the sulfate is in the form of magnesium sulfate, then CSH can be attacked. Okay, so CSH plus magnesium sulfate, CSH will become, this is the gypsum plus magnesium hydroxide plus silica gel. So CSH will lose its strength. Okay, and some other type of chemical reaction. So if the sulfate is in the form of magnesium sulfate, it will be more severe because CEE688 could be detected. For delete etching guide formation, we mentioned of this type of soft attack. We talk about steam curing for concrete. That occurs when temperature is high. Okay? So etching guide is destroyed or dissolved into sulfate and aluminate. So you can move to other part of the concrete. Then the temperature drop down, etching guide may form again, which may cause expansion and cracking. Okay, we'll talk about that more in a moment. We also have a so-called somosite formation. Okay, somosite is a natural mineral which is similar to the product from sulfate attack. So that is breakdown of CSH with sulfate and also carbonate ions. Okay, so that is a special type of sulfate attack called somosite formation. Right, then let's look at some of the picture for sulfate attack. This is the scanning electron microscope. Sulfate attack in porous concrete. Etching guide deposit around sand grain. Okay, so here the scale is 100 micrometer. Okay. This is the sand particles. This is the cement paste. Okay, if we zoom in this square, we see here the picture on the right. So the picture on the right show etching guide, which has this strip pattern where we see white and black patterns, okay, like a zebra. Okay, so this is etching guide from SEM picture. Okay, and we see on the boundary between the sand and the cement paste, etching guide is deposited. Here is, again, etching guide deposited within a former cement grain. Okay. Remember when we talk about hydration of cement paste, we have a different type of CSH. So one of them is called heavy grain. In the heavy grain, the original cement grain is hollows out because of the diffuse, dissolve, diffuse, and precipitate, right? So we have some empty space within that cement grain. And that's where the etching guide deposit. Okay, so whenever there's an empty space, there's a voids, the etching guide may form there. So again, this is the etching guide, which has the strip pattern. We have black, white, and black. So here is SEM of sulfate attack in porous concrete. Okay. All calcium hydroxide is dissolved and removed. Okay. So calcium hydroxide tend to deposit in the ITZ, which is the boundary between aggregate and cement paste. If the pH level is lower than 12.4, calcium hydroxide will be dissolved, leached out. So leave the empty space. Remember, the black color in scanning electron microscope is the empty space, it's the voids. Okay, so we can see clearly in the ITZ we have a lot of voids. That is because calcium hydroxide is leached out. So sulfate attack on dense impermeable concrete. Okay. If the concrete is impermeable, has very, very low permeability, okay, we may see a deposit of so-called brucite. So brucite is the name of mineral for magnesium hydroxide, MgOH2. And also gypsum near the surface of the concrete, which in contact with groundwater. And some aggregate may produce on the surface, but the penetration is not very deep, is very limited. Okay. As we can see from here, so this is concrete on the right. This layer is G, it's called G is for gypsum. Okay. And M is for brucite, which is magnesium hydroxide. And we can see the layer of magnesium hydroxide and gypsum is formed on the surface of concrete only. So the damage is limited on the outside. That tells us if we can control the permeability, make the permeability of concrete low, then soffit attack can not really do a great damage. So even though this concrete mortar is exposed to magnesium sulfate, and we know from the previous equation, for magnesium sulfate, CSH may be active. Okay. So for magnesium sulfate, CSH may be active, but still, if the permeability is very low, the damage is limited. Okay, so that's one of the key things we want to prevent soffit attack, make the concrete less permeable. So here are more words about delayed action-guide formation. Okay, let's just read it together. Some form of distress in concrete with steam-cured concrete because the temperature is very high, or we have thick section. For thick sections, we have high temperature inside the concrete because concrete is a good thermoisolator and hydration heat cannot dissipate easily. So then the concrete temperature may be very high. So that's a potential place for delayed action-guide formation. Okay. And here it says reasonably high cement sulfate content is usually involved. Okay. And exposure of the concrete to prolonged moist condition is necessary. So which means we need moisture for DEF to occur. So that's why steam-cured concrete is prone to have DEF for two reasons. One, the temperature is high, so action-guide can be dissolved. And secondly, we have moisture. We have prolonged moisture condition when the concrete is under steam curing. So the symptom of DEF is expansion, cracking, and spalling of outside of the concrete. And for pre-stressed concrete, we may have loss of pre-stress for the rebar or debonding of pre-stressed cables. Okay. And the last sentence is very interesting. So in most field concrete examples, DEF seems to be associated with prior ASR. Okay, ASR we know is alkali silica reaction. We discussed ASR in the first lecture of durability series. Okay, so DEF seems to be associated with prior ASR, even though ASR may not be very severe. Okay, why that's the reason? Okay, we're going to talk about that in a moment. Okay, and here shows what we already know. Study shows that earlier heating results in destruction of action-guide. So the action-guide is dissolved, destroyed. And for a prolonged period of time, there's no crystalline, which means there's no AFT, action-guide, or AFM, monosulfide aluminate in concrete. Okay. And moderate amount of sulfate remain in the pore solution, but most of the aluminate and sulfate from ethylene guide would absorbed by CSH. Okay. And after prolonged wet exposure, so again, moisture is necessary for DEF, ethylene guide will reappear. Okay, so ethylene guide is formed again, which will cause expansion, cracking of concrete. And the start of formation of ethylene guide is almost always associated with leaching of alkali hydroxide from the concrete pore solution into the wet surrounding. Okay, that's why wet condition is necessary. So alkali hydroxide need to be leached out of concrete before formation of ethylene guide. Again, why that's the case? And monosulfate is virtually absent throughout. So there's no typical formation of ethylene guide from monosulfate aluminate as we know of. Okay. Ethylene guide, again here in the boundary between cement paste and aggregate. So here we see the ethylene guide found in cracks. Okay, so whenever we have empty space in concrete, ethylene guide tend to form there because before ethylene guide is formed, it is in liquid form. Yeah. And also the ethylene guide here in the ITZ. Okay, we can see the classic streak pattern. Right, so this is the ethylene guide filled cracks. Okay, in the DEF affected concrete. Let's see, where is the ethylene guide? Here. Streak pattern also here, and also here. This formation of ethylene guide. So when ethylene guide formed, volume is expand. So that will crack the concrete along the crack and also along the ITZ. So here we talk about the correlation between DEF and ESR. Why the prior ESR before DEF will set up the formation of ethylene guide. Okay. So prior ESR will set up the deposition of ethylene guide, okay, because ESR will consume alkali. Okay, remember for ESR, it is reaction between alkali in cement paste with reactive silica in certain type of aggregate. So during ESR process, the alkali is consumed. Okay, so when the alkali hydroxide concentration is reduced, then ethylene guide will form. So here is the reason. So ethylene guide is unstable at high pH value. Okay, so when pH level is very high, the ethylene guide will not be formed because it is unstable. When alkali is leached out due to ESR or some other reason, and then ethylene guide will become stable. So we can see formation of ethylene guide. So that's the reason prior ESR will set up the DF. So the second paragraph, in lab studies using non-ESR susceptible aggregate, this cannot happen. Immersion of specimen into a wet environment will cause same effect. Okay, when we immerse the concrete specimen in a wet environment, the alkaline hydroxide will be leached out of the specimen. So pH level is lower, then ethylene guide become stable. So we have a DF. Okay. So any questions for that? Okay, so DEF and air voids. So in the field DEF conditions, air voids in concrete often are filled up with ethylene. Okay, so let's make very nice pictures, as we're gonna see in the next slides. Okay, but this will reduce the expansion because the air void is empty. We form ethylene inside the empty air voids does not cause too much stress, tensile stress in concrete. So that may reduce the potential cracking. But here it says the freeze-out resistance of concrete may possibly be compromised. However, why? Okay. Before we answer that, let's look at the picture. So this is ethylene filled in the air voids. Okay, so very nice picture. Again, ethylene is here. Black, white strips. Okay, so very easy to recognize ethylene in the SEM pictures. So when the empty air void is filled up with ethylene, then the effectiveness of these air voids to reduce freeze-out damage is reduced. Why? Because the air is filled up with ethylene. So when ice form, because freeze-out damage, there's no more room for ice to fill in. So that's why it says the freeze-out resistance may be compromised. Okay, so far we talked about the mechanism of different type of software attack. So how we can control software attack? The most important thing we can do probably is to reduce the concrete permeability. Okay, so we can do many things to reduce the concrete permeability, okay, such as using low water cement ratio, silica film, and so on. Okay, we can also use low CEE688 cement. Okay, so that's the classic method to reduce software attack. That's how we produce type 2 and type 5 cement, right? By reducing percentage of CEE688. Okay. But that may not be very effective for certain type of software attack. Okay. For example, if the sulfate is in the form of magnesium sulfate, then CSH can be affected. Then using low CEE688 cement will not be very effective. We can also use pozzolands such as slag and flash and silica film, okay, that convert calcium hydroxide into CSH. Okay. So that means we have less gypsum. Okay. That means we have less ethylene formed. Also, pozzolanic reaction will reduce the concrete permeability. Okay, so that is the number one most important thing to control sulfate attack. So use pozzolans if possible. And of course, if we can limit the exposure to sulfate, that's very helpful, of course. And here talk about sulfate attack and type 5 cement. So type 5 cement is a sulfate resisting cement. So that limit the amount of CEE688 to less than 5%. Okay. The idea is to limit the amount of ethylene that could be formed and protect the concrete from sulfate attack. But some researchers consider this is not very effective because first, the ethylene can be formed from not only CEE688 but also C4AF. Okay. And also, they think denser concrete, no matter the type of cement to make the concrete, will undergoes very little damage. Okay. Because the sulfate solution from groundwater cannot penetrate easily into dense concrete. So again, we think the most important thing is to reduce the permeability of concrete. So this thing, the use of type 5 cement, if we do not restrict the water cement ratio, will not be very effective to prevent sulfate attack. Okay? Because if you only use type 5 cement, but you make the permeability very high by using high water cement ratio concrete, then sulfate attack could still do damage inside the concrete. All right, so that's about sulfate attack in general. Any questions before we jump to the next topic? Okay. All right, so far we have discussed freeze-all damage, we discussed ASR, corrosion of reinforcement, and sulfate attack. Okay. So the biggest challenge facing concrete research about studying concrete durability is the time scale. Okay. So typically, if a concrete will develop durability issues, it will take years or even decades in the field. Okay. But how we can find out if a certain type of concrete will susceptible to certain type of attacks? Okay. You know, researchers develop different type of standard, okay, from ASTM, from ACI. Okay. For example, for ASR potential of the concrete, we have ASTM C1260 and 1293. Okay. One is for mortar bar test, another one is for concrete test. For 1263 is called ASTM accelerated test. Okay, so we make some mortar bar, and we put the mortar bar in very harsh environments. Very high temperature, I believe is around 80 degrees Celsius. The concentration of alkali is very high. Okay, so we put the specimen in this harsh environment for only 2 weeks. And if the algae is susceptible, then the bar will expand. So we measure the change of length in the mortar bar. Above certain level of expansion, we say the algae is not good for ASR. Okay. So we did some of these tests for some of our local algae, and we found out the expansion above certain value. So we say we cannot use the algae. Okay. However, in reality, we have used that type of algae for many, many decades, around 40, 50 years. But we never see ASR in the real situation. Okay. So that means the ESTM standard give us a false positive. Okay. The reason for that is we want to see the result fast. So we similar to this, we want to see if we can boil egg into chicken. Sorry, we put the chicken in 99.5 degrees Celsius for 3 weeks. Okay, and then we can see if we can hatch egg. But if we cannot wait 3 weeks, and we put the egg in boiling water, but for only 5 minutes, and every time you can see, boiled egg. Okay, you cannot see the result. The real result. So the biggest challenge is the time scale. How we can see the result in a reasonable short period of time. Okay, several weeks, months, or even a couple of years. The common element in durability problem is water. Okay, internal saturation with water, okay, and penetration of external water will be the reason for all type of attacks, from corrosion of reinforcement, from ASR, freeze-thaw damage, soft attack, delayed action gap formation. So we know all of these attacks will involve with water, either from outside or inside of concrete. Okay. So providing and maintaining a low water content by, for example, reduce the water cement ratio. Okay. So that is trying to limit amount of internal water. Or we can do a tight concrete, which means we reduce the permeability of concrete. If we reduce the permeability of a concrete, we can prevent the external water from getting inside and do the damage. So concrete permeability is the most important factor to control the concrete durability. Basically, the lower the permeability, the better durability. Okay, we can make the concrete more durable, last a longer time. So the factor controlling concrete permeability, including size of the crack, so that's including micro crack and also macro crack. For cement paste, if we reduce the water cement ratio, we can make the pores more unconnected. So that may reduce the porosity and the permeability. Okay. But if the concrete cracks due to high shrinkage, we know when we discussed concrete shrinkage of concrete. So for low water cement ratio concrete, we may see more autogeneous shrinkage. If the concrete crack because of that, then the permeability will be high. Okay, no good. If we increase the water cement ratio, the porosity will be higher, and also the pores will be interconnected. So that will increase the permeability. Degree of hydration. Longer time, we have more percentage of cement hydrated. So we have more hydration product. So the permeability will be lower. For aggregate, typically it will be more impermeable compared to cement paste. A certain type of aggregate, they may have higher permeability compared with cement paste, okay, depending on many factors. So how we can assure a tight structures? Okay. So we can do many things. Yeah, we can reduce the water cement ratio. So that will limit the porosity in the cement paste. Okay. But when we do the reduce the water cement ratio, make sure the concrete can be fully compacted by using, for example, super processor. Okay. So we can also incorporate blending component, which means flash, slag, or silica fume. Okay. So that may also reduce the permeability, or proper finishing and curing to seal the outer surface. Okay. So evaporation of water from the surface will be limited. And also make sure the concrete does not crack due to many reasons. Okay. For example, if we design a high strength concrete with very low water cement ratio, so the pore structure may be very dense, but if the concrete cracks due to autogeneous shrinkage, then the water and harmful materials will penetrate easily through the cracks. So that will be no help. So crack prevention is very, very important also. So here shows how the size of the crack will affect serviceability of concrete. So when the size of the crack is small enough, the crack may even heal itself, because we almost never have 100% of deep hydration. We always have some of the unhydrated cement. Okay, So when the size of the crack is small, the crack may heal itself. Okay. So for ACI, the limit for the size of crack is around 0.013 to 0.016. Okay. So below that is called controllable leakage. Above that, we have visible leakage about 0.333, so 1/3 of inch, corrosion will likely to occur. So from previous discussion, we know permeability is number one, the most important factor for durability. And here shows many different methods to measure permeability of concrete. So we'll pick some of them to discuss. Okay. So the first one is water permeability test. So that measure how easily the water can penetrate the concrete. Okay. For example, here we generate some type of crack in concrete by applying a load, and then we measure how easily solution can penetrate through the specimen. Okay. So that is based on the famous Darcy's law. Okay. So dq dt is the so-called rate of fluid flow. So that is a function of permeability coefficient. So delta H is the pressure gradient to the pressure head. A is the surface area, the cross-section area for the specimen. Mu is the viscosity of the fluid, the water, and L is the thickness of the solid. So based on this, we can measure everything except the K value. So we can calculate the permeability coefficient from the measurement of delta H, A, mu, and L. Okay. And for that example, we can draw something like this. This is the size of the crack. So we increase the size of the crack, the permeability coefficient, the K value will be increased. Okay. And here is the ACI limit for the size of the crack. So we can measure the water permeability in concrete to assess the durability. The next method is used very often. It is called rapid chloride permeability test, or the RCPT test. So this is one of the ASTM standard tests. So that's the setup for the test. So we have a concrete specimen. On the top and bottom side here, it is coated with epoxy. For the other uncoated side, we have two different types of solution. Okay, 3% sodium chloride and 3.3 molar of sodium hydroxide. Okay. And then we apply a potential difference electrical charge, and we measure the total charge in coulombs after apply the potential for 6 hours. So the more total charge pass through the concrete, the more permeability the concrete has. Okay, and based on the total charge after 6 hours, we can give a different classification for concrete permeability. So this is called chloride permeability test. Okay. So this is an example study using the RCPT test. So here shows the volume fraction of coarse aggregate. We change the volume fraction of coarse aggregate, and we measure the total charge after 6 hours. Okay. In this study, we see if we increase the volume of coarse, the permeability will be lower. Okay. The reason for that is, when we increase the amount of coarse aggregate, we also increase the amount of ITZ, which is the interfacial transition zone. So ITZ is the weak point in concrete. So the more algate we put in concrete, we have more ITZ. So that makes the concrete more permeable. Okay, so increased coarse aggregate content, permeability of concrete will be lower. Okay. The next several slides will show us the correlation between the strength of concrete, the water cement ratio of concrete, and the chloride permeability of concrete. Okay. So the first one is the strength and W over C. Right. Clearly, if we increase the water to cement ratio, the strength will be lower. Okay. So that's true for all different type of aggregate. So MSA is for maximum size of aggregate. Okay. For the same water cement ratio, we can see if we reduce the size of aggregate from 3/4 inch to 3/8 inch, the strength will be higher. So that is because if we reduce the size of aggregate, we reduce the stress concentration because the modulus of elasticity of aggregate and cement paste are different. So reduce the size of aggregate, we reduce the stress concentration around ITZ. So concrete will crack later. Okay, so we know that already. But if we increase water cement ratio, the strength will be lower. So we also know that. So clearly, we have strong correlation between water cement ratio and the strength. Here shows how permeability is affected by water cement ratio. Okay. What we can see here is if we increase the water cement ratio, the permeability tend to increase. Okay. But the correlation is not as strong as the water cement ratio to the strength. Okay. For this one, lower water cement ratio, higher strength, very clear. But here, not as strong because for the water cement ratio of 0.45 to 0.5253, the difference for permeability is not as strong as the previous. Okay. And then let's look at the correlation between strength and permeability. Okay, so not much a trend we can see of. The y-axis is the strength, the x-axis is the total charge after 6 hours. That is the permeability. So this figure tells us if we increase the strength of concrete, you cannot guarantee the concrete has a lower permeability. So strength should not be used as the indicator, at least not the sole indicator for durability. Okay, because strength cannot really control the permeability. A concrete with higher strength cannot guarantee the permeability will also be lower. Okay, remember, permeability is the real deal, is the real factor controlling concrete durability. It's not for strength. How about the size of aggregate? I think this is the old slides. When we increase the water cement ratio, the permeability will be higher. So that's true for all different aggregate size. But if we keep the water cement ratio constant, we increase the size of aggregate, permeability will be higher. Okay? So that is because for larger size of aggregate, we have more ITZ, and ITZ tend to be weaker. Okay. So increase the size of aggregate, we have weaker ITZ. That's the result of bleeding, okay, and also differential strains when the concrete is under stress. So that will translate into higher permeability for concrete. So how we can reduce the concrete permeability? We can optimize the mix design of concrete by using water cement ratio, but that's not only factor. We can also reduce the size of aggregate or reduce the volume of aggregate. We can use pozzolanic materials that will increase both the strength of concrete and also reduce the permeability of concrete due to pozzolanic reaction. We can use proper curing and the manufacturing process so that will increase the alpha, degree of hydration, reduce the entrapped air, so that will reduce the porosity, reduce the permeability. We can use surface coating. Okay? If we can do that, use polymer, for example. And we should use crack resistance design by using shrinkage, reduced diameters, or fibers to reduce the size of the crack. Excuse me. Okay. So here shows effect of different admixtures. Okay. So all the concrete has the same water cement ratio. Okay. If we use silica film, okay, that will reduce the permeability because pozzolanic reaction and also the filler effect for silica film. Slag, even more effect, okay, because slag not only has pozzolanic properties, but also hydraulic property. But also hydraulic properties. Latex, okay, we'll talk about latex modified concrete in future lectures, but latex can greatly reduce the permeability of concrete. So how we can make a durable concrete? First thing we need to remember is durable concrete is not equal to high strength concrete. So only reduce the water cement ratio, you cannot guarantee the concrete be more durable. Okay. One of the major reasons is high strength concrete is more susceptible to autogeneous shrinkage. Okay. Because lower water cement ratio for high strength concrete, that will increase autogeneous shrinkage. If the concrete crack, the water will easily get inside and do the damage. So remember, deterioration is associated with water ingress. Okay, so water can do the damage itself due to freeze-thaw damage, for example, and the water will also bring the harmful materials such as chloride for corrosion, sulfate ions for sulfate attack, and so on. And permeability is not directly related to water cement ratio like the stress. Okay. So simply control the water cement ratio is not enough. So what we should do? So we should not only worry about strength. The strength is important because that will ensure concrete will resist design stress without failure. And also a stronger concrete can make the crack less likely. The second important thing is the permeability criteria. Okay? So that will ensure concrete provide limited flow penetration to reduce the water and also harmful ions related to different type of attacks. And finally, the crack resistance criteria. Okay, that is the toughness of concrete. So when concrete crack due to different reasons, how the concrete can ensure the size of the crack will not big enough, or how we can, bridge the crack by using, for example, fibers. Okay. So we'll talk about fiber reinforced concrete when we talk about high performance concrete. Okay. So how we can reduce the size of crack is also important. So to design a durable concrete, we need to worry about three things: the strength, the permeability, and also the toughness. All right, so the key idea for the last three lectures, we have three lectures for concrete durability is what is the role of water in durability? Okay, water will involve with all kinds of physical and chemical attacks. Okay. And what is the mechanism and how to reduce frost damage, scaling damage, ASR corrosion, and sulfate attack. Okay. And what is the relationship between permeability and durability? So remember, the number one factor control concrete permeability, durability is permeability. Okay, that's the end for today. I will also assign us the second homework. I think sometime next week. Okay, so that's it for today's lecture.